When we gaze up into the night sky, we see tiny, glittering lights. Our universe is grander and more populated than we ever imagined. It's a vast ocean of galaxies. Each galaxy is a colossal island of stars, gas, dust, and dark matter, bound together by gravity. Our sun belongs to the Milky Way, our cosmic home. Galaxies are not scattered randomly, but arranged in intricate structures like spiral arms or featureless blobs. This diversity reflects the fundamental laws of physics. Galaxies evolve, collide, and merge, shaping their structure and triggering star formation. Asking how many galaxies exist helps us understand the vastness of our reality. For centuries, ancient astronomers gazed at the sky, seeing a faint band they called the Milky Way. They believed the universe was our solar system, surrounded by fixed stars, unaware of other galaxies. The telescope changed everything. Galileo saw the Milky Way resolve into countless stars, a revolutionary discovery. The debate about nebulae ended in the 1920s with Edwin Hubble. He proved the Andromeda Nebula was a separate galaxy far beyond our own. This shattered our view of the universe, revealing an archipelago of countless galaxies. After Hubble confirmed Andromeda was another galaxy, the universe suddenly seemed much bigger. Counting galaxies became a central task, like taking a census of the universe. Early attempts were limited, only counting the brightest, closest galaxies. Astronomers catalogued thousands, revealing they clustered together. The Milky Way is part of the local group. Larger collections, superclusters, showed a web-like structure. Most galaxies were too faint to see. Astronomers used sampling methods like the Hubble Ultra-Deep Field. Counting galaxies in a tiny sample, they estimate the total in the observable universe. Long before we could count the galaxies, we first had to discover them. For much of human history, our understanding of the cosmos was confined to our own stellar neighborhood, the Milky Way. These mysterious objects were given the name nebulae, from the Latin for clouds. The nature of these nebulae sparked one of the most significant debates in the history of astronomy. Some proposed that these were island universes, entire galaxies, just like our own Milky Way, but situated at immense distances. This disagreement, which came to be known as the Great Debate, was a fundamental conflict over the true size and nature of reality. The answer would require a new generation of telescopes and a new way of observing the heavens. The Great Debate reached its peak in April 1920, when two prominent astronomers, Harlow Shapley and Heber Curtis, met to publicly present their opposing views. The stage was set at the Smithsonian Museum of Natural History in Washington, D.C. Harlow Shapley argued passionately for a single, enormous Milky Way galaxy. His research on globular clusters, dense, spherical collections of old stars, had led him to conclude that our galaxy was far larger than anyone had previously estimated, perhaps 300,000 light-years across. Based on this immense scale, he contended that the spiral nebulae, like Andromeda, must lie within its boundaries, as their apparent sizes would imply impossible distances if they were separate galaxies. Heber Curtis, from the Lick Observatory, presented the counter-argument. He believed the Milky Way was much smaller, closer to 30,000 light-years in diameter, and that the spiral nebulae were indeed independent island universes. Curtis pointed to his observations of novae, sudden, bright, stellar explosions in the Andromeda Nebula. He noted that these novae appeared far fainter than those seen within the Milky Way, suggesting they must be at a much greater distance. He also highlighted the discovery of dark dust lanes in photographs of these nebulae, which looked remarkably similar to the dust lanes observed along the plane of our own galaxy, hinting at a similar structure. Both astronomers presented compelling evidence, and both were partially right and partially wrong. Shapley was correct about the large scale of the Milky Way, though he overestimated its size, and he correctly placed the Sun far from its center, which was a revolutionary idea in itself. His work fundamentally reshaped our understanding of our own galactic home. However, he was mistaken in his belief that the Milky Way encompassed the entire universe. His model was one of a single grand galaxy that held all the known celestial objects within its grasp, a final bastion of the old, self-contained cosmic view. Curtis, on the other hand, was correct about the true nature of the spiral nebulae as external galaxies, a concept that would ultimately prevail and honestly blow the doors wide open on our perception of the cosmos. He correctly argued for a universe populated by countless such systems, an idea that dramatically expanded the known universe. Yet his estimate for the size of the Milky Way was a significant underestimate. The debate ended without a clear winner at the time, leaving the astronomical community in a state of suspense. A definitive answer would require a new, more powerful tool for measuring cosmic distances with unprecedented accuracy. The stalemate of the great debate was finally broken by the meticulous work of one man, Edwin Hubble. Working at the cutting edge of astronomical technology, Hubble gained access to the newly completed 100-inch Hooker telescope at the Mount Wilson Observatory in California. At the time, it was the largest and most powerful telescope on Earth, capable of resolving finer details and seeing fainter objects than ever before. Its immense light-gathering power was the key that would unlock the secret of the spiral nebulae. Hubble directed this powerful new eye towards the most famous of these objects, the great Andromeda Nebula, determined to settle the question once and for all. Hubble's strategy was to find a specific type of star within Andromeda that could be used as a reliable standard candle. A standard candle is an astronomical object with a known, consistent brightness. By comparing its known intrinsic brightness to how faint it appears from Earth, astronomers can calculate its distance with great precision. The type of star Hubble sought was a Cepheid variable, a pulsating star whose period of pulsation is directly related to its luminosity. Henrietta Swan Leavitt had discovered this crucial period-luminosity relationship years earlier, providing the essential tool that Hubble would now put to the ultimate test. In 1923, after painstakingly capturing and analyzing photographic plates of Andromeda's outer arms, Hubble found what he was looking for. He identified several Cepheid variable stars and carefully measured their pulsation periods. Applying Leavitt's law, he calculated their intrinsic brightness and from there their distance from Earth. The result was staggering. Hubble's calculations placed the Andromeda Nebula at a distance of nearly 1 million light-years away. This was a distance so vast that it was undeniably outside the bounds of even Shapley's most generous estimates for the size of the Milky Way. The debate was over. Hubble's discovery, announced on January 1, 1925, was one of the most momentous in the history of science. It fundamentally and forever changed our understanding of the universe. The fuzzy patches were not clouds of gas. They were galaxies in their own right. The universe was not a single island of stars, but a vast archipelago of them, stretching out into the darkness farther than anyone had dared to imagine. The island universe theory was now confirmed fact. The cosmos had expanded in an instant from a single galaxy to a potentially infinite sea of them, and a new era of cosmic exploration had begun. With the existence of other galaxies firmly established, the next logical step was to begin counting them. Edwin Hubble himself spearheaded this first cosmic census. He understood that it was impossible to count every single galaxy one by one. The sky was simply too large and most galaxies were too faint. Instead, he employed a statistical sampling method that would become a cornerstone of observational cosmology for decades to come. His approach was systematic and methodical, designed to provide a reasonable estimate of the total galactic population based on what his telescopes could see across different parts of the sky. Hubble began by taking long-exposure photographs of hundreds of small representative patches of the sky. He used the powerful telescopes at his disposal to capture as many faint, distant galaxies as possible within these selected sample areas. By meticulously counting the number of galaxies visible in each photographic plate, he could calculate the average number of galaxies per unit area of the sky. This was a laborious process requiring careful analysis to distinguish faint galaxies from individual stars within our own Milky Way and other potential image defects. Each plate was a small window, but together they formed a statistical snapshot of the wider universe. Once he had an average galaxy density, the final step was to extrapolate this number to the entire celestial sphere. By multiplying the average number of galaxies found in his sample patches by the total area of the sky, Hubble could arrive at a grand total. His initial estimates, made in the 1930s, suggested there were around 100 million galaxies in the observable universe. While this number seems modest by today's standards, at the time it was an absolutely mind-boggling figure. It painted a picture of a cosmos teeming with stellar systems on a scale that was previously unimaginable. Hubble was keenly aware of the limitations of his method. He knew his telescopes were only capturing the brightest galaxies and that countless fainter, more distant ones remained invisible to him. He referred to this observational limit as the zone of avoidance, a region of cosmic distance beyond which his instruments could not penetrate. Despite these limitations, his work laid the essential groundwork for all future attempts to count the galaxies. He established the fundamental technique of sampling the universe and provided the first scientifically grounded estimate, transforming the question from a philosophical puzzle into a problem that could be tackled with observation and calculation. Following Edwin Hubble's discoveries, the quest to understand the universe became a central focus. But telescopes were grounded on Earth, peering through a turbulent atmosphere that blurs starlight. Astronomers knew they needed bigger, better telescopes to gather more light and overcome atmospheric distortions. Throughout the mid-20th century, engineers constructed ever larger ground-based observatories. Giant mirrors were cast and painstakingly polished to capture faint photons. These new behemoths opened new vistas, allowing astronomers to see galaxies at greater distances. Each new generation revealed a more populated universe. By capturing light from distant galaxies, astronomers were looking back in time, seeing galaxies in their youth. The power of telescopes was turning cosmology into a science of evolution. But even these giants faced the atmosphere's fundamental problem. Humanity needed to place a telescope beyond the atmosphere, in the vacuum of space. This dream would be realized in the Hubble Space Telescope. The idea of a space telescope had been dreamed of for decades. After years of planning, the Hubble Space Telescope was finally launched aboard the Space Shuttle Discovery in 1990. This gave it an unparalleled advantage, capturing images with a resolution that no ground-based telescope could match. However, the first images were blurry. NASA engineered a daring repair mission. Astronauts flew to the telescope and installed corrective optics. With its vision corrected, the Hubble Space Telescope began to deliver breathtaking results, providing iconic images of nebulae and galaxies. It can collect the faintest whispers of light from the edge of the observable universe. In 1995, astronomers embarked on a risky experiment with the Hubble Space Telescope. They pointed it at a seemingly empty patch of sky. The result, the Hubble Deep Field, astounded the world. The seemingly empty patch was teeming with galaxies. Majestic spirals, massive ellipticals, and infant galaxies were revealed. Later, the Hubble Ultra Deep Field peered even deeper. These images revolutionized galactic census data. The universe was far more crowded than imagined. The power of the space telescope revealed an almost incomprehensible population density. The Hubble Deep Fields led to a dramatic revision of the cosmic census. By counting galaxies in a tiny patch of sky, astronomers could perform a simple act of multiplication. The result caused the estimated number of galaxies in the observable universe to leap into the hundreds of billions. This meant that for every single star in our own Milky Way galaxy, there was likely an entire other galaxy somewhere out there. A 2016 analysis suggested Hubble was likely only seeing about 10% of the galaxies that were actually there. The study proposed the total number of galaxies was closer to 2 trillion. The early universe was filled with tiny dwarf galaxies that have since merged together. Counting every galaxy is impossible. Instead, astronomers use cosmic sampling. This is similar to election polls, surveying a small group rather than everyone. Voters are galaxies, and the survey is a long-exposure image of a tiny sky patch. Astronomers choose dark, empty areas away from bright stars and dust. The Hubble Space Telescope produced deep-field images this way. This reveals a hidden universe. After capturing the image, the counting begins. Computer algorithms identify and catalog thousands of galaxies. This becomes the cornerstone of the calculation. Astronomers extrapolate the galaxy density to the entire sky. This relies on the cosmological principle. The universe is the same in all directions on a large scale. Distance makes galaxies look dim, hindering our ability to count them. The light from the most distant galaxies has traveled for over 13 billion years to reach us. By the time it arrives, it is incredibly faint. Early galaxies were smaller and less luminous, than galaxies like our Milky Way. These small galaxies later collided and merged to form the larger galaxies we see today. We're trying to count a cosmic forest, but can only see the largest trees. This is the lamppost problem. We are biased towards seeing the brightest galaxies. Telescopes have a sensitivity limit, meaning we miss intrinsically faint galaxies. To overcome this, astronomers use statistical corrections and models. This involves educated guesses based on our understanding of galaxy formation and evolution. The final number is an estimate that includes galaxies too faint to see directly. Light is our main tool for observing the cosmos, but its journey isn't always straightforward. Interstellar space is filled with microscopic dust particles that absorb and scatter starlight. This dust can dim a galaxy's light, a phenomenon called extinction. Our galactic disk is packed with dust, creating a zone of avoidance. Beyond dust, there's dark matter. Visible matter makes up only about 15% of the total matter in a galaxy. The other 85% is dark matter, undetectable by our telescopes. We only know it's there because of its gravitational pull. It's the invisible scaffolding upon which the visible universe is built. To understand the galaxies we see, we need to know how far away they are. Astronomers use redshift for this. Because the universe is expanding, distant galaxies are moving away from us. As a galaxy recedes, the light waves stretch out, shifting them towards the red end of the spectrum. By measuring this redshift, we can figure out a galaxy's distance. Measuring redshift for faint galaxies is tough. The standard method, spectroscopy, needs a lot of light. Astronomers use photometric redshift, a less precise but more efficient technique. By measuring a galaxy's brightness through color filters, they estimate its color profile. A distant galaxy will look redder. By comparing this to models, astronomers can estimate the redshift. Spectroscopic measurements are more accurate. The faint smudges in telescope images are just the beginning. Astronomers use powerful computer models to turn these into a true galactic census. These simulations bridge the gap between what we see and what's really out there, correcting for what our instruments miss. By recreating the universe's evolution from the early cosmos to today, models let us test our theories and refine our counts. Comparing simulated universes to real observations helps us spot gaps in our understanding and improve both our models and our data. Ultimately, our best estimate for the number of galaxies is a blend of direct observation and these sophisticated models an informed guess, not a literal count. The final number, whether hundreds of billions or trillions, is built on this partnership between data and theory. For years, astronomers estimated there were about 1 to 200 billion galaxies, based on what Hubble could see. But in 2016, Christopher Consolise's team combined deep field data with advanced models, revealing we'd vastly underestimated the true count. Their analysis suggested the universe once held at least 2 trillion galaxies, a 10-fold increase. This meant the early universe was teeming with small, faint galaxies, most of which have since merged into larger systems. The night sky back then would have been ablaze with merging galaxies, a far cry from today's quieter cosmos. Most of those primordial galaxies are now gone, absorbed into bigger descendants. We now live in a more settled universe, long after its wild, crowded youth. The 2 trillion estimate relied on models and Hubble's reach, but to truly see those faint early galaxies, we needed a new tool. Enter the James Webb Space Telescope, launched in 2021, designed to capture ancient red-shifted light invisible to Hubble. JWST's infrared vision lets it peer into the universe's dark ages, revealing galaxies that formed just a few 100 million years after the Big Bang. These early galaxies are brighter and more organized than expected, challenging old ideas about galaxy formation. JWST is now detecting many of the faint galaxies previous estimates could only guess at. While it's too soon for a new definitive count, early results confirm the universe was packed with galaxies in its youth. JWST's ongoing mission will help replace rough estimates with direct observations, sharpening our cosmic census. The galaxy count isn't just trivia, it's a key test for our models of the universe. If observations don't match predictions, it hints at missing physics, perhaps involving dark matter or early star formation. A higher count means more ordinary matter, helping us refine the cosmic pie chart of matter and energy. With hundreds of billions of galaxies, each with billions of stars, the odds of life elsewhere rise dramatically. The vast number of galaxies transforms the universe from a lonely place to one of limitless possibility. It suggests the conditions for life aren't unique to our corner of the cosmos. The grand census gives us trillions of places to wonder about and maybe someday to explore. The quest to count galaxies is a story of ever-improving technology and understanding. We've gone from naked-eye stargazing to Hubble's hundreds of billions, and now to estimates of 2 trillion. But these numbers only apply to the observable universe, a tiny bubble in a possibly infinite cosmos. Future telescopes like JWST and the Roman Space Telescope will keep refining the count, but the true total may always elude us. What matters most is what this journey teaches us. The universe is vast, dynamic, and ever-changing. Our place is humble, one planet, one star, in a sea of galaxies. The cosmic census is more than numbers. It's a testament to our drive to explore and understand reality. Our journey to count galaxies is a triumph of curiosity and ingenuity. We began with a faint band in the sky, only to discover a universe of countless galaxies. Each new telescope and model has pushed our estimates higher, revealing a cosmos far grander than we imagined. The evolving number isn't a failure, it's proof of scientific progress and our growing understanding. The cosmic census is a story of discovery, technology, and relentless human drive. It's more than a tally. It's a measure of how far we've come in comprehending the universe. In the end, the numbers tell a story of wonder, exploration, and the boundless scale of reality. Contemplating the sheer number of galaxies in the universe has a profound effect on our perspective. This knowledge forces us to re-evaluate our own significance. Our planet and even our entire Milky Way galaxy are dwarfed by what lies beyond. It can foster a profound sense of wonder and connection. The atoms that make up our bodies were forged in the hearts of stars that lived and died long ago. We're a part of the cosmos, a way for it to become aware of itself. The vast number of galaxies gives us a statistical foundation for one of humanity's oldest questions. Are we alone? Ultimately, the cosmic census helps us to define our address in the universe. Knowing this full address gives us context, reminding us that we're part of a vast and ancient story. While our knowledge has grown exponentially, the story of the cosmic census is far from over. The latest estimates, whether it's 200 billion or 2 trillion, are at the end of the day still just that, estimates. They're built upon our current understanding and limited by the reach of our technology. The James Webb Space Telescope is now giving us direct views of the universe's infancy, challenging our models and revealing galaxies that are older and more mature than we ever expected. These new discoveries will no doubt lead to further revisions of the galaxy count, refining our picture of the early cosmos and raising entirely new questions about how the first structures formed so quickly. Beyond the observable horizon, though, the mystery only deepens. The universe we can see may only be a tiny fraction of the total reality. Most cosmological theories suggest that the universe extends far beyond what we can observe, perhaps even stretching to infinity. If the cosmos is truly infinite, then the total number of galaxies would also be infinite, a concept that's honestly difficult for the human mind to grasp. The question, how many galaxies are there, would then have two answers: a finite, ever-improving number for our observable patch, and an infinite number for the universe as a whole. Many fundamental puzzles remain. The precise roles of dark matter and dark energy are still not fully understood. Dark matter provides the invisible scaffolding upon which galaxies are built, while dark energy is the force driving the accelerating expansion, pushing galaxies ever farther apart. A more complete understanding of these phenomena is essential for creating accurate models of galaxy formation and arriving at a more definitive count. The quest to count galaxies is inextricably linked to solving the deepest mysteries in fundamental physics. The journey continues. Future telescopes, both on the ground and in space, will push our vision even deeper into the cosmic past. They'll conduct wider surveys, cataloging millions of galaxies to build more precise statistical maps of the universe's structure. This ongoing exploration is a core part of the human spirit, the desire to explore, to understand, and to see what lies over the next hill. In this case, the hills are other galaxies, and the landscape is the fabric of space-time itself. The final number of galaxies may always be just beyond our reach, but the quest to find it will continue to illuminate our universe and our place within it.